Hello everyone, this is a tool demonstration for BNSynth that addresses the bounded Boolean functional synthesis problem. Boolean functional synthesis or BFS is a well-known challenging problem in the domain of automated program synthesis from logical specifications. Since Boolean functions are the basic building blocks of modern digital systems, BFS has many applications such as program synthesis, circuit repair, QBF stat solving, and many more. Now let us define the BFS problem formally. In Boolean functional synthesis, we are given with a relational specification f of x comma y that relates the input variables x to output variables y. And we are supposed to synthesize Boolean functions for each of the output variables, represented by psi of x, and referred as column functions. BFS is limited in a way that it aims to find some column function and puts no restriction on the size of the formula. However, in certain applications like circuit repair or circuit synthesis, resource constraints such as number of gates and the chip area plays a critical role, thus making it important to have a concise formula. This motivates the bounded BFS problem where we aim to synthesize column functions under a given bound on the formula size. And this is where our tool BNSynth steps in. Let us look at the overview of our tool architecture BNSynth. BNSynth takes two inputs, BFS specification and the bound on the clauses. For example, consider the BFS specification to be f of xy equals to x0 or y0. And say we put a bound on the number of clauses to be k equals to 3. The question here is that can we learn a column function within the specified bound? BNSynth is the first tool to the best of our knowledge to solve the BFS problem by specifying a bound on the number of clauses. BNSynth uses neural counterexample guided technique to solve this problem, which is essentially a data-driven approach, and hence the first phase in the tool is to collect samples to train our underlying model. We use Manthan's weighted sampler to generate satisfying assignments from the given specification f. In our example, we get the samples as shown in the table on the left. As an extra step, we remove ambiguity from data to facilitate learning. For example, consider x0 to be 1. In this case, we have two possible valuations for y0. This may impede learning, and hence we remove one of the rows. This gives us the final training data with just two rows. In the training phase, the model takes x0 as the input and approximates y0. We'll come back to the training part later. Once the training is over, we get a candidates column function. For example, a candidates column function can be negation x0. Since the candidates column function may not satisfy the specification, we verify this using Manthan's verifier. To verify, Manthan constructs the error formula and checks for satisfiability. If the error formula is unset, it means we get the valid column function. Else, the verifier will produce a counterexample. These counterexamples are then added to the existing training data, and the model is trained again on this updated data set. This iteration is performed until a valid column function is found. In principle, our approach is guaranteed to terminate based on certain heuristics that we consider. In the training phase, we use a neural architecture called Gated Continuous Logic Network or GCLN to perform linear regression on the training data. GCLN helps us to succinctly represent all combinations of Boolean formulae under a given bound on the size of the hidden layer K. The formula can be in CNF or DNF format, but for our discussion, we'll be focusing on CNF. For a given bound K and the number of inputs mod x, the total number of CNF formulae that one can get is upper bounded by 2 to the power 2 mod x plus 1 times k. For example, the architecture shown here having k equals to 3 and mod x equals to 1 can compactly represent 2 to the power 9 possible combinations of formulae. Amongst these, which combination of formula is selected depends on the weights of the neural network, which we call as gates. For example, if these weights are activated, that is their value being equal to 1, then we get the candidate's column function to be negation x0. To represent a discrete CNF formulae in the continuous domain in order to facilitate learning, GCLN uses special activation functions such as gated T norms for conjunctions and gated T conorms for disjunctions, defined as shown. For more details on these, one can refer to the GCLN paper. Now let us look at the working of our tool BNSynth by running it on one of the LUT benchmark. Consider the benchmark with 5 inputs and 2 outputs. One can run our tool BNSynth using the script called bnsynth.sh. It takes 4 arguments as input. The first one is the benchmark name. Second one is the bound on the number of clauses. The third one chooses between CNF or DNF formula format. And the final fourth argument selects the architecture to train. Let us first consider the CNF case and train it for the given benchmark with 10 clauses and architecture 1. Once the training is done and the error formula is unset, we get the column functions for the corresponding output variables. In the table below, we show the comparison of our tool BNSynth with Manthan. One can clearly see that BNSynth gives 3 times improvement on the number of clauses and 4 times improvement on the number of literals compared to Manthan. Similarly, one can also run BNSynth for the DNF case by changing the argument from CNF to DNF. In this case, we get the column function in the DNF format. At this point, we don't compare BNSynth and Manthan for the DNF case. To summarize, these are the features of our tool BNSynth. I would like to highlight that we have 2 more architectures for both CNF and DNF, which we have not covered in the video or paper. You can run these architectures by pulling our tool from the GitHub link. Thank you.